Hello everyone. I'm presenting on behalf of the team that collects all the what I consider really interesting information, and that's only because I'm stupid and I don't understand any of the seismic stuff. So for the seismic guys in the audience, I do have a couple of slides that explains just a little bit about what the different types of isotopes are, what they can tell us, and how we calculate the various terms that you can use, that you see on these isotope maps that we produce. But the data that I'm presenting today has been collected as part of the Exploration Incentive Scheme funding, and it also stretches back several decades, well before my time. So just some key take-home points. Isotopic contour maps, which are some of the things that I'm going to be presenting today, some of the summary maps. They're a bit like a geochemical X-ray of the crust, a bit like paleogeophysics. They give us an image of the crustal architecture in ancient times rather than what exists currently today. So it's really interesting to compare what we might image in ancient times versus what we image in the present day. But basically these isotope contour maps, they help us recognise but also quantify old ancient crust versus juvenile mantle derived crustal domains. And in this picture, in this map here, which is a crustal residence age map, which I'll explain what that means in a couple of slides. Basically the green areas denote parts of the crust that haven't sat around very long, versus these pink and purples and even yellows are parts of the crust that have sat around for a very long time and been constantly recycled. So these maps we can use to reveal lithospheric architecture. So you can see some of these different isotopic domains align quite nicely with major cratonic or terrain boundaries. And they reveal things like ancient faults, craton margins, and also things that we might not be able to see by current day geophysics. The important things about these, which I'll show towards the end of my talk, is that they're time resolved, so we've got an age component to them. We can actually do time slices and track how these structures and the lithospheric architecture evolved with time. And what you can see in this map, just overlain on top of it, is the location of operating and historic gold, nickel, and also lithium or tin tantalum lithium mines. And you can see that most of them correlate to these juvenile isotopic domains. So there's a strong link between juvenile isotopic domains, long-lived deep-seated lithospheric structures, which are focusing fluids and metals and causing them to be deposited within these domains, and the location of these mineral deposits. So these isotope maps have long been shown to be a powerful exploration tool for targeting when you combine them with things such as geophysics and also a lot of other geological data sets. So just a quick history of what we've got currently and what we've got upcoming that's going to be released within the next 6 months. In the yellow here are the location of all of our currently published uranium-lead geochronology ages, mostly zircon, which tells us the age of the crystallization of that rock, whether it was magmatic, whether there's been metamorphism that's affected it. We can date the rims, we can date sediments and work out the sources of those sediments and also the depositional age of them. In the orange here is a new layer that's going to be released in the next couple of months in GeoView, and this is a compilation of existing what we call external geochronology ages. So there's almost 800 ages across the state, which represent igneous crystallization, sediment deposition ages, and importantly, dated mineralization events. So these are sourced from published literature, student theses, MARIWA reports, anything that we could find that we could quantify and QA/QC the data, we have captured in a database, and this will be released in the next couple of months. In the black here are all our whole rock samarium neodymium isotopes, which we use to make many of our isotope maps. We've got over 2,500 sample points across the state, and we've increased coverage by at least 10% in the last 4 years. And the green here are our hafnium isotope sample locations. And again, this data set since the last release in 2022 has increased its coverage by 30%. So we're going to have a much more updated map and a lot more coverage when we do our time slices. On top of that, we have oxygen. Again, we've increased coverage by about 30% in that data set, and a new data set that we're currently working on in conjunction with Curtin University is lead isotopes within K Feldspar. So we're going to have over 400 locations across the state, and we hope to be able to make some isotope maps for those. So we routinely collect these isotope data sets, and these help us to understand and track WA's geological evolution. And they're interesting on their own, but when they're combined, they tell us a whole lot more. So just a little crash course in isotopes and what they tell us. There's all these certain terms like epsilon and crustal residence ages and two-stage depleted mantle model ages. And it's all a bit of a mouthful, but basically magmas inherit their isotopic signatures from the mantle that was originally melted to form rocks that then may have been melted again, and also the crust that they melt on their way up to upper crustal levels. So a rock's isotopic signature and the minerals that crystallize within it, specifically zircon, basically act as a fingerprint, and they can tell us if it formed from new mantle material or recycled ancient crust, which could be both mafic or metasedimentary, or potentially a mixture of both. So just in very simple terms, if we're looking at rocks that have remelted a lot of crustal material or material that's been at the surface and interacted with meteoric water, we tend to have what we call more evolved isotopic signatures. So we'll have more negative epsilon hafnium and epsilon neodymium values. We'll have older depleted mantle model ages, older crustal residence ages, and we have heavy or very positive oxygen isotope values. And the difference is when we look at something that's come straight from the mantle or been derived from a mantle-derived melt, we typically have more juvenile signatures, which have more positive epsilon hafnium and epsilon neodymium values, younger depleted mantle model ages, younger crustal residence ages, and oxygen values that should be within this range if it's come from the mantle and hasn't interacted with anything else. And just a quick 1 minute, because I don't have much time, these terms that we use, epsilon hafnium, epsilon neodymium, depleted mantle model ages, single stage versus two stage, and also crustal residence ages, there's a lot of assumptions that go into these. The main thing that is the most useful is actually the crystallization age of the rock. So that thing is a robust absolute age, whereas everything else that we calculate has a whole lot of inherent assumptions built into it. So we calculate epsilon hafnium and epsilon neodymium by basically coming back towards a chondritic uniform reservoir. So if you change that value, you change the epsilon hafnium value. And then if we start calculating depleted mantle model ages, if we have different crustal evolutionary paths with different ratios or values that we use within those, that'll give us a different model age. So the point that I'm trying to make here is that there's a lot of assumptions in these values. It's not the absolute ages that matter, it's the relative differences. So the bigger the data sets we've got, the more we can compare between old versus young. And a crustal residence age just is basically our depleted mantle model age minus the magmatic crystallization age, which gives us an idea of how long that material has been sitting in the crust. So we use two-stage depleted mantle model ages because they're better, that they're not as influenced by the depleted mantle age. The single-stage model age, it gives us the ages at which that material has been extracted from the mantle and then sat in the crust and evolved along one of these various paths here. And we also use crustal residence ages to make our pretty isotope maps. And I thought I'd just put up a couple of pictures of the evolution of isotope maps. They've gone from being extremely rainbow coloured to slightly more subdued, and we may even change the colours that we use going forward, but you can see that we've actually increased our sample coverage quite considerably in less than 20 years, and that's giving us a lot more detail in terms of different isotopic domains. So the Q isotope domain we can see coming out, but within our most recent maps, which has a lot more sample coverage, we're able to delineate these a lot better. So these maps of the Yilgarn help us reveal ancient and juvenile crustal domains. So we've got juvenile crustal domains here, which overlap nicely with mineralization, versus more ancient ones up in the Naria, and also the boundaries that separate them. And if I just go to the next one, the key thing that we can do now, because we've got age constraints, uranium-lead age constraints, and a lot more sample coverage, is we can actually start doing time slices. So these are three different time slices. This is for the Yilgarn for samples greater than 2.73 GA, samples between 2.73 and 2.67, and samples less than 2.67. And you can see that the younger signal dominates. It's overpowering the older signatures. But you can actually, now that we can do these time slices, and the other important thing to note here is that these are actually dated mineralization events that we can also overlay with our isotope contour maps for these time slices. We can actually start seeing differences in how potentially the lithospheric architecture has evolved through time. So this is JP's 170 kilometre LAB boundary. You can actually start thinking that this potentially is being recognised as way back as 2.73, which is kind of exciting. The north-south terrain boundaries through here and through here, maybe not quite so apparent in the pre-2.73, but we need a lot more spatial coverage. We've only got 200 samples here versus over 500 in the younger slice. But this shows you the importance of integrating the isotopes as well as the uranium lead age constraints, so we can actually start pulling together time slices and understanding the evolution of the lithospheric architecture through time. And one other thing that we can do is actually plot the data up and image it through time versus this is a two-stage depleted mantle model age versus the crystallization age of granites. So when we use that in combination, this is for hafnium values, and every single point represents a median value for a granite that we've analysed. What I'm showing here is that for the U&Me, and also in particular the Naria, the granite ages here between 2.6 and 2.75 have very old depleted mantle model ages. This is just recycling very, very old crust. The U&Me, we're looking at about 2.9 to 3, which is a similar age to the depleted mantle model age. These are probably relatively juvenile and primitive to start with, but over time have progressed to more crustal reworking in that U&Me terrain and southwest terrain. But if we overlay the eastern goldfields, we can see that the trend is different. It goes to more primitive compositions, and you can actually just start working out little blips where it goes to much younger two-stage depleted mantle model ages at about 2.7, 2.65, which overlap nicely with the dating of gold mineralization events, and these probably represent mantle input events at this time. So we're trending towards more juvenile mantle-derived input events rather than crustal recycling, and then once that 2.65 happens and we head towards keratinization, we do start to do just crustal recycling. There's no more mantle inputs that are observed, at least in that data set. So again, I'll leave it at that. I've covered these already, and please come and see me at my poster on the wall, and I can talk you through crustal residence ages, two-stage depleted mantle model ages, and anything else isotopic that you'd like to chat about.